Welcome back to the Beginner Game Programming Series. I'm Chili, and this is Lesson 21. I think I told you in the last lesson that today we're going to be doing dynamic memory allocation. Well, that was a lie. That was a big fat lie, because I forgot about one little detail that I wanted to show you guys. And that little detail is rendering text. Yeah, that thing. So, I know you guys are not really interested in text. I mean, who needs text, right? But I'm going to show you guys anyways. So, I'm going to need you to take the sprite folder, the one we made in Lesson 21, and copy it and make a new one. We'll call it font. Okay? Get that font going. And I'm also going to need you guys to download the zip file, lesson21.zip. And in here we have a couple of bitmaps. We're going to copy those bitmaps to the project folder inside the solution folder. Right? You have a solution folder, which is the main folder that holds the whole solution, and then you have the project folder. That's weird. Let me get rid of that. Alright, so let's take a look at these bitmaps for a second. So this is the font that we're going to be using in this tutorial. Now if you take a look at it, you might notice a few things. First of all the characters are of the same width. This is what is called a fixed width font. And that's important because it makes our job a lot easier for rendering the font. Most other fonts, like Times New Roman and so forth, they're variable width. I forget what you call them, but anyways, depending on the character, there will be a different amount of space allocated. For example, a lowercase I is gonna take up a lot less space than, say, an uppercase W or something like that. So those kind of fonts are a pain in the ass, so we're not going to use them. We're going to use a fixed width font. Every character has the exact same dimensions of space. In this case, this font is the fixed cis font, and its dimensions are 16 pixels wide by 28 pixels tall. So that's the first thing. The second thing you might notice about the font is the order in which the characters appear. If you're familiar with ASCII, you'll know that this is the same order as that. It doesn't have all the ASCII characters, mind you, just the ones that are important for rendering, normal text, dialogue, stuff like that. So it starts with the space character, which is just a big blank, and it ends with the tilde character. And there's a blank at the end. It's 32 characters wide, 32 characters per row, and there's 3 rows. So a total of, 96 if you count the blanks. And this is the font, like I said, that we're going to be using in the lesson. So let's open her up. Good, that's lined up with my recording window. Very nice. I don't know what this is. Why are you open? Alright. We'll get rid of that. Alright. So we got we should have we have our walking dude demo here. Very nice. And we want text. So how are we going to do this? Well, let me just go back to this image here for a second. Go to console us. No, fix this. There we go. So in the last episode, what we did was we we had a bunch of separate bitmaps and we loaded them onto separate surfaces. Well, logically separate surfaces. It was actually all in one big array, but logically they were all separate surfaces with a pointer to each surface. In this case, we have all the characters. I mean, letters. These letters are characters. They're just sprites, right? All they are is sprites. The white is going to be transparent. It's not going to be drawn, and the black is going to be the part that is actually rendered. And the only difference between these sprites and the other ones is that these ones are smaller, and these ones they all exist on a single bitmap. So in this exercise, we are going to load them onto a single surface, and then we're going to copy them from that surface to the back buffer when we draw the characters. So we could have done that for our animated dude, but I chose, in that example, I used separate bitmaps, separate surfaces. You can use a single bitmap on a single surface too. You can use a single bitmap, separate surfaces. You can mix and match. So I'll show you how to do it when all your sprites are on a single surface. This works for, characters and whatnot, like animated characters as well. In this case, we're using glyphs, but it can work for any sprite sheet that you download from the internet. You can also use similar techniques to manage them. Alright, so the first step is actually loading the font object. So first we're going to have to create a structure that'll represent our font. So we'll go d3d graphics.h and let's create a new structure here. Struct font. Alright. So font structure is going to have int car width, int car height, right? The width and height of an individual character. Int number of characters per row, and d3d color, pointer to surface. Now I think that is enough to specify our font. We don't need a color key because all our fonts are going to be black and white, and you'll see why in a second. That doesn't mean that we can't draw text in color. So yeah, width and height of an individual character, number of characters per row, and the actual surface. Now that should be sufficient. Now we're going to do a load font function. So we'll rename this font. This will be font pointer to font. Font surface file name. Copy that, paste it. Copy, paste. I'm just going to make it a normal int. Normal int here, and we don't need a key, but we do need something here. We need int n cars per row. Alright, now it's time to actually implement the function. So we'll go here. It's going to be about the same as a load sprite function, right? I could probably copy and paste this. We'll reuse our load bitmap function. Very convenient. And we'll do font pointer to car height is equal to car height. Right. Font car width equal to car width. Pointer to n cars per row is equal to n cars per row. There. Alright. Oh, wait. Not to forget. Surface is equal to surface. Right. We have to actually load the surface here. Well, we load the surface here, but we've got to set our pointer to the loaded surface now. Okay, so that's all we need to load the font into our font structure. Now we want to be able to draw a character onto the screen. So, void draw car x int y font pointer to font, not front, font. There. Alright, let's get on with it. So far so good. It's pretty straightforward. This is like I said, it's very similar to drawing a sprite. Well, but it's going to be a little bit different though, because now we have to when we had in the draw sprite situation, every sprite in this function, every surface of a sprite is its own pointer, so everything always starts at the origin, right? But in here, we don't know where the character starts. It can be starting in the middle of the bitmap, the first row, the second row, right? We don't always start at the top left corner and go to the bottom right when we're copying it to the back buffer. We only want to copy a portion of the surface to the back buffer. Ah, shut up. Wait a second. Shut up. Thank you. Alright, what was I saying? Oh yeah, so it's going to be a little bit different than the draw sprite, but I think we'll be able to handle it. I'm just going to copy and paste this though. Dangerous, and yet I will still do it. Okay, so why? So what are we going to be doing here? We need to figure out our start point and our end point for copying. So first thing we need to do is we need to figure out the index of our character from the draw character is missing a very important thing here. We need the actual character we're going to draw to the screen. That would help. Game.cpp. Where are you now? Not game. D3D graphics. And I also have to do this. D3D graphics. There. I always forget that. Alright. So first thing we need to do is we need to calculate our index from our character. Car C. Now what do I mean by index? Well, I'm just going to keep this open from now on, because I use it. Index means the index of the character in our bitmap or our sprite sheet here. So this would be index 0, 1, 2, 3, 4, right? This would be index 32. This would be index 64, right? This is index 95, 94. But that does not match up with our character value, because the space character in non-hexadecimal in ASCII is actually 32. It's not 0, it's 32. So we need to convert our ASCII code into our index on our sprite sheet. So what we do is we go I want to make all my integers constant because we're not going to be changing them. Constant int, what else? What should it be? Sheet index is equal to C minus space. So we subtract the value of the space character from C, and that means that if we have space, right, if C is equal to space, then we have space minus space, and which is 0. So the index for space becomes 0, and accordingly the index for all the other ones will be the right index for our sprite sheet. Next, now we have our index. We need to find the row and column number based on our index. So constant int we'll say column is equal to sheet index we'll do sheet column. It's equal to sheet index mod. I said mod. Font pointer to what? N cars per row, right? So again, we have 32 characters per row. So if our index is 1, then 1 mod 32 is 1, right? So we'll be in column 1. If our index is 32, that would be here, then 33 mod 32 is 1, right? Still in column 1. So that'll give us our column number, no matter which row we're on. And the same idea, fucking thing's freezing up. Oh, good. Constant int sheet row equal to sheet index divided by font pointer to n cars per row. And this will give us, of course, it will give us what row we're on. Now we have our row and our column. Now we need our start positions. Constant int start, we'll say x start. Now our starting x position is equal to sheet column times font pointer to car width, right? Constant int y start is equal to what? Sheet row times font pointer to car height. There. So that'll give us the starting x and y pixel coordinate on our sheet. So if our index is, again, if it's 33, then our starting pixel will be somewhere around here, I guess. Right. That'll calculate our start and our... And now we need our finish. Constant int y end, no, x end is equal to x start plus this. We just add the width of one character there. And constant y end is equal to y start plus here. I don't have to make these constant. I don't want to explain that. It doesn't hurt to make them constant because they're not supposed to change throughout this function. So it's not a bad idea to make them constant. But it doesn't change anything if I get rid of the const here. All right. So now we have our x start, y start, x end, y end. And that should be enough We need one more. Well, I'll put it in later. Okay, so now we have y is equal to y start. As long as y is less than y end, y plus plus. X is equal to x start, x end, x plus plus. There we go. Very simple. Now, this part is going to be a little bit different. Actually, I'm going to add another D3D color. I'm adding another parameter. The color of the character to be drawn. So unlike a sprite where its color depends on the color of the bitmap, for fonts we're going to make it so that you can, for the same bitmap loaded into memory, you can render it to the screen with any color you want. And this is how we're going to do it. What we do is first we check to see if font pointer surface at x plus y times, and here we want the width of the surface. We can pre-calculate that. Constant int surface width is equal to font pointer to car width times font pointer to n cars per row. We just pre-calculate that up here, so we don't have to pre-calculate it for, we don't have to calculate it for every single pixel. We just have to calculate it once and then we're done. A little bit of optimization there, just a teensy weensy bit. Surface width. So we check to see if the font is equal to, we'll do it the proper way, D3D color underscore XRGB and 0, 0, 0, right? So that's black. Black means that we want to put a pixel. And then we just put our pixel here. I should change the name here. This should be X off. It should be Y off. Otherwise it's going to collide with this X and Y. So X plus X offset, Y plus Y offset. And then we just draw, we put color. So the color that's being put on the back buffer has nothing to do with what's on the actual surface, right? We don't reference the surface at all when we're putting a color. We just use the surface to determine whether we should or should not put the color. So in this case, it's not really a image as so much as it's a mask. This thing here is a mask telling us where we should draw and where we shouldn't. But we do not look at this to determine which color we actually draw. Alright. So that is it. I'm going to tell you right now this won't work properly because, well, there's a bunch of mistakes. Maybe you've seen them already. Maybe you haven't. But you will see them soon. There's actually a problem that there's a bug in the code from lesson 20, and that will give us a problem here. But anyways, let's test it out anyways. Okay, so to test it out, first we have to go to game. We got to add a couple of new user variables, or at least we have to add one new one. Font. Oh, we need two more. We need the surface that will hold the font sprite sheet. So D3D color font surf. And its size is going to be 512 because that's the width of the thing by 84 24, I think it is. If I'm wrong, well, then we'll be in trouble. And we need an actual font. So we're going to call this one Fixed Sys. Okay. Now we got to load the font. We go down here. Load font. Okay. And Fixed Sys. Our surface is font surf. Our file name is, I think it was Fixed Sys. Oh god. 16 by 24.bmp. I'm just guessing. Width of a single character is 16, height is 24, characters per row is 32. There we go. So that's all we need to do to load a font. And then we're gonna draw it. So we'll her up here. Draw graphics dot draw car. There. Character will be P. Start at 00. Font will be and Fixed Sys. Color will be D3D color underscore XRGB 0 1 255 0. There. Copy that. Bam, 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 bam. Yeah, I think you know what's coming already. I think it was 16. So this one's 16. 32. We have to move the 40, 48, and 64. Right. We've got to move the position over for every character, otherwise we'll just be writing on top of each other. P-U-B-E. S. Alright. So let's draw some pubes on the screen. And we failed because of bad stuff. Now I have to do it for every single one. There we go. Let's try it again. Build. Succeeded. And let's see, let's reap the whatever. Debug assertion failed. F read. Alright, okay. I probably got the wrong file name. Okay, what do you want? Fixed sys.bmp. What's the real file name now? Fixed sys 16 by 28 bmp. 24. Right. It's not 24, it's 28. Okay. Let's try it again. There we go. So we've got our dudes walking and we've got our text, and it's looking, well, it's looking pretty shitty actually. That does not look like text at all. It's not even lined up where it should be. So, what's the problem? Can you guess? At this point, I would recommend that you don't just keep going on watching, and instead you should pause the video and try to figure it out for yourself. What's wrong with all of our code here? It's a good exercise in debugging. But for those of you who lack that sort of testicular fortitude, I'm about to reveal to you what the fuck is wrong with our shiz. So first thing we're gonna do is we're gonna hit a breakpoint, because breakpoints are where it's at. Draw car. So we'll put a breakpoint here. And we're gonna make sure all of our shit is in order. So sheet index. So our character is a P. Sheet index is 48. Seems plausible. I'll just make sure. This one's 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 48. Alright. Good. Next, if I can get my program to stop freezing up like a dick. Like a bag of dicks. Or I guess it won't. So, wait a sec. Thank you, program. Alright, so index is fine. Next thing, sheet column 16. Makes sense. 32 plus 16 is 48. And row, where's row? 1. That's right, it's the second row, so that would be row 0, row 1. Okay, let's keep going. X start is at 256. Seems plausible again. 256 pixel. And Y start is at the 28th pixel. That seems correct. X end is 72, Y end is 56. And the surface width is 512. So, all's well that ends well, right? Not quite. So here's the problem. We're going to draw our P. The first thing we do is we look at surface X plus Y times surface width. Doesn't actually show us that calculation, but it seems like it should be correct. So what's the problem here? Do you see it yet? I guess you don't. Let's put a breakpoint there. We'll continue until we hit this breakpoint. So now we're going to put a pixel on the screen, right? And we don't even have our screen thing yet. Wait a second. I'm going to take off this breakpoint here. I'm going to run. Now I'm going to come back here. I'm going to run here. I wanted to run through once so we could draw the screen. It doesn't draw, does it? Damn it. Oh, right, because we're not finished drawing all of the characters. There's 5 characters in a single frame, so I have to continue 5 times. 1, 2, 3, 4. P-U-B-E-S. P. Okay, here we go. We're on the 3rd frame now. We'll continue here. So now if we look at our screen... damn it, it still doesn't show it. That sucks balls. Well, whatever. We'll have to figure it out without looking at our game screen. Alright, so the basic idea is this. We're starting to draw, and we should be drawing at the top left corner, because X offset and Y offset are equal to 0. So we should be drawing at about the top left-hand corner of the screen, depending on where the first pixel is actually in that character. So what we do is we add the X offset to X and Y. But this is a big problem, right? Because X and Y are the X and Y in our sprite sheet, and they're way over here. So if you add our X offset on the game screen, say this is the game screen here, this screen. If you add our X offset and our Y offset, which are 0, to our X and Y position in our sprite sheet, you're going to get a character that's down here somewhere, right? And that is not what you want. So X and Y in this loop only refer to X and Y in our sprite sheet. But they don't make that much sense for the X and Y in on the actual screen. So what we want to do here is we want to subtract X start, and we want to subtract Y start. Okay? Because X and Y on the screen, they still have to move, right? They still have to scan from right to left when we're drawing. But we want them to start at our offset. We don't want them to start wherever they're starting in the bitmap. That would not be a good idea. So we subtract the X start and the Y start from here. We start off in here and then we subtract it out of here. And that's how we'll handle that situation. Now by doing this, we should have fixed the position problem. Let's stop. Let's restart. Alright, now our text looks like it's about in the right spot. But it's still freaking garbage here. That looks pretty fucked up. So, what's the problem? Well, you can debug this code all you want. You won't find the problem because it's not in here. Believe me, I tried. I did a dry run of this before I'm recording, and I run into this problem, and I was like, what the fuck? What's the problem, bro? And the problem happens to be that there's a bug in our load bitmap code here. But I didn't realize that. So I was believing because the load bitmap, it worked fine for our sprites. I just took it for granted that there was no problems with it. But after banging my head against my desk for about 15 minutes trying to figure out the problem here, finally I decided, okay, I've got to check this bitmap out. I've got to make sure that it's loaded properly. So what I did, we can't use our draw sprite to draw the whole bitmap because it takes a sprite. So I made a quick function in here. Void test. Void. And I just defined it like right in here because I didn't care. I'm just going to delete it afterwards anyways. And what the test does is, actually it has to take a surface, D3D, color pointer to surface, right? And all it does is it just draws the surface onto the screen. So I'm going to find my draw sprite function here. And we'll go here, just copy that, tab that over. Okay, now we know our height is 84 and we know our width is 512. We're not going to test or anything. We're just gonna draw the mother. Draw this mother. X, Y. Let's draw in the top left-hand corner. And our color, fuck you. Color is surf at X plus Y times 512. And this very simple function will allow us to test out our loaded surface. Make sure it's working properly. Success. And we go down here and we will comment selection. Go graphics dot test and font pointer. Alright, it's not called font, it's called fixed sys. Pointer, what the fuck, bro? No, right, it's not a pointer, it's just a normal object here. Okay, and we need the address. Oh wait, surface is an address, right? It's a pointer. Good. Okay. That's good. And here is our text. And as you can see, it's got that slanty problem here that we had before, which is indicative of this being fucked up in the neighborhood of, what's it called? Padding. So the padding is fucked up on this, bro. Right. Which is strange because these guys loaded fine. So why is this one not loading? So then what you got to do is you got to go into bitmap. And you put a breakpoint here. Run that mother. And you get padding bytes per row. And you look at our info header.width times 3. So info header.width is 50. Does that make sense? 50? Shouldn't it be 512 pixels? All right, this, okay, yeah. This is for loading the sprite. I forgot. Duh, this is the sprite. Let's do it again for the font. I said do it again. Why are we loading bitmap so many times? Now I'm confused. All right, because we have the sprite dude, he has a bunch of frames, right? So we got to load for every single frame of him. Okay, I get it. I get it. I think he's got like 14 frames of animation. Or oh, wait. I didn't want to do that. No! Damn it. Clicked one too many times. 3, 4, 5, 6, 7, 8, 9, 10. Okay. 11, 12, 13, 14. There we go. Okay, now we're on our font sheet. Our font bitmap. And so width is 512. Now, the thing you should know about 512 is it is a multiple of 4. So obviously if you multiply by 3, that will still be a multiple of 4. So because it's a multiple of 4, let me just get up my trusty thingamabob. Here we go. Alright. Because it's a multiple of 4, let's, fuck that. Fuck you, bro. Just deselect that. Okay. Let's just make a little thing here. Right. So here's a single pixel, right? And let's say we've got another pixel coming in from here. And we got lots of pixels here. And this is a 4-byte aligned unit of 4, right? And if this is the end of our file, we don't want any padding, right? Because we end right on a 4-byte boundary. So we don't want any padding. That's the case of what do you call it? The row width being a multiple of 4. All right. But in this case, if it's a multiple of 4 and we mod 4, a multiple of 4 mod 4 is equal to 0. 4 minus 0 is 4. So what we're saying here is we need 4 bytes of padding. So in the case of ending right on the boundary, our algorithm thinks that there's going to be 4 bytes of padding, when really there should be 0 bytes because it's perfect, right? It doesn't need any padding. It's lined up perfect. But because the way I wrote the algorithm, it works for the case of where it's not properly aligned. But in the case where there shouldn't be any padding, it adds 4 bytes instead of 0. So what we need to do here is we need to add another mod 4, right? So this means that if there's 3, 2, or 1 bytes of padding in this calculation, it will just be 3, 2, or 1. But if it calculates that we need 4 bytes of padding, it will return 0 instead, because 4 bytes, that's stupid. That means that we have a perfect alignment and we shouldn't have any padding. Alright, that was a little bit of an explanation there, but it's kind of complicated. Alright, so now we fixed the bug in our load bitmap function. This, by the way, is the reason why you shouldn't be coding. Normally, I would never code a load bitmap function myself. I would just look it up on the internet and use some API function. The reason why we did this is because it's a good exercise for a learning programmer. But in a real program, I would never use my own load bitmap. I would use one from, for example, GDI Plus or something like that. It's much more robust and you don't get stupid errors like this. So it's fun to make your own functions, but when possible you should use pre-existing stuff. And this is why, because you make mistakes. Alright, let's start without debugging. And now we have our bitmap and it's being copied properly to the screen. So it's loaded without any problems, and it's all beautiful. So now, if I go graphics.h, I can delete my test, because we don't need to test anymore. And now I'll go to game, I can delete this. And I can uncomment this. What do we got here? So I'll just show you guys that you can change the colors of your characters at will here. And if I start without debugging, now we have pubes. And if you look, when this guy's head makes it over here, you'll see that it is it's transparent, so it shines through. The stuff below it you can see through these characters. Alright, and the letters, they look properly aligned to me, more or less. So, yeah, that's that. Let me just try something here. If... No, I better not. I'll probably crash the program if I do that. Well, let me try it anyways. If mouse dot is in window, plus mouse dot get mouse x. Get mouse y. Ha! There we go. I'm just fooling around now. We'll copy that. Bam, 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 bam. There. Let's try it out. There we go. Pubes! Pubes! Look how it follows my mouse pointer like that. It's beautiful. It's poetry in motion. Mouse pointer's a little blinky, but that's weird. Strange. Right. So now let's crash the program. Bam. Abort. All right. So that's how you draw a character. Now I'm going to take a short break, and when I get back, we're going to write a function that will draw a whole string to the screen, and then we'll run a little test, and we'll also learn we'll learn how to use the timer object that's been in the framework but hasn't been used. So I'm going to take a break. I'm just going to pause the video here, and for you guys it'll only be about 3 or 4 seconds. For me, I'm going to go to bed, and I'm going to wake up tomorrow, and I'm going to do some more tutorial recording. Yay! Yay! Another 2-hour-long video. Let's hope not. All right. So I'll see you guys in about 10 to 12 hours. Well, let's continue, shall we? Let me think. Can I remember what we were doing last time? I think we just perfected our draw char function, and let me just make sure. Yeah, it's working fine. Beautiful. Let's get away from there. Yeah, okay. So the next thing we want to do is, well, if we look at this is kind of a pain in the ass. If we have to call draw char for every single character that we want to put on the screen, it's kind of like the situation we had before with put pixel and compiled sprites. It's just not a good scene. So what we want to do is we want to make a function that will let us draw a string to the screen in a single function call. That'll make life a lot easier. But before we do that, we have to fix the draw char function just a little bit. See, draw char, if you look at our sprite sheet for our font, we know that we can only draw characters from the space character here to the tilde, or to this character here, the character after the tilde, right? Any characters outside of those will probably break our function, because we'll have an index which is either a negative number, not good, or is outside of our bitmap, also not good. So what we need to do is we need to first test whether C is within our sprite sheet, our font. So if C is less than... Damn it, now I can't find my... Where is it? There it is. Get it. C is less than space, or if C is greater than... tilde, return. So this just makes sure that we're within our character sheet. And if we're not, then we just leave right away. Otherwise, we do some good stuff here. Alright. Now, it's time to make that function for drawing a string to the screen. Now, I recommend that you stop the video right here and try to make it yourself, because it's not that difficult, and I don't know, it's better if you do stuff than just have me spoon feeding everything to you. But if you don't, if you don't have the cojones for that, I guess you can watch me do it. Draw a string. Alright. We'll do a constant char pointer, because we're not modifying the string, the array in any manner. String. What's string? Yeah. Nah, I'll call it string. What else do we need? Okay, we're going to draw the string. So we need the string, we need the X and Y coordinates, we need the font, and we need the color. There. So like I said, it's going to be a very simple, straightforward function. Put it in here. Do a little copy paste. Don't forget to put your scope resolution operator in there. Fuck you. There we go. Okay, so it's a very simple process. For int, I guess x is equal to what? Damn it. I'm gonna have to call these one x offset, y offset. So we'll start off at x offset as long as wait. That's not what we want to do at all. Index. We're not going to be looping through our x position. We're going to be looping through the index in our character array. So as long as index is equal to 0, as long as string at index is not equal to I could just put not equal to 0, but I'm going to put the null character there explicitly. String index plus plus. There. So we'll loop through our through the indexes into our string until we reach the null terminator. And for every character that we encounter, we are going to do... What am I doing here? This isn't game. This is wrong. There we go. Drawstring. What are we doing? Draw car. So the character will be string at index. The x offset is going to be x off, our starting x position, plus index times font pointer to car width, right? So as we move right in our string, we're also going to move right on the screen to make room for the new characters. And y is not going to change, so we'll just do y off. Font is just font, and color is color. And that is all she wrote. That's all we need. Very simple. Let's test it out here. Make sure I didn't make any stupid mistakes. I did not. Surprisingly enough. I'll delete that. That too. And here we're going to do draw string. Yeah. And pubes. The rest is fine. Put that there. There we go. I'm tired of the green pubes. Let's have some red pubes. It's the only way to tell a real redhead from a faker. Gotta look at those pubes. Alright. Looking good. So we got the same behavior as before, but we did it in one line instead of 5 lines or 6 lines. Ah, yes. The glory of being able to text and stuff. There. Alright. So that's it. With this, you can do a lot of good stuff in your games and stuff. And if you want bigger text, you just gotta make a different font. I made this in Photoshop. It wasn't that difficult. It's just a little pain in the ass figuring out how to space them correctly. These are all just typed out on a single line, but to space the individual lines is a little more work. Now, here's what we're gonna do. We're gonna use this. We're gonna use our new found capabilities of rendering text to do something interesting here, a little experiment, if you will. We're going to use the timer class here, and we're going to use it to benchmark our program. We're going to see how long it takes to do drawing operations. The timer class is very simple. You just create it, and then you call start watch to start the timing, stop watch to stop, and then you can get time milli to get the time that was recorded. To get the time that passed between start and stop. And it gives you a floating point value. That's the time in milliseconds. So let's do that. First thing we want to do here is, if I go to my game.h, we're going to add the timer in here. Timer does not need anything for initialization. So here's what we do. Before we start drawing our sprite instances, we'll call timer dot what? Timer. Right. If we're going to use the timer, we have to include its header file. So # include timer.h. No, there. Good. Now, timer dot, yes, start watch. There. And timer dot stopwatch. Alright. We'll get rid of this mouse thing here. That's not necessary. That is not necessary. Okay, so what we want to do now is we want to be able to render text onto the screen, but we have to format a number into the text, right? Because we're going to get a floating point number out of this timer.getTimeMilli. And we want to format that into a text string and draw it on the screen. Now, if we were doing console, we would just do printf, right? But we're not doing console. So can you remember what we have to do? I'll give you a hint. We did it in lesson 20 when we were opening files up, right? We had to open files up procedurally. Right. There. Looping through all of the indexes into our sprites. We'll give 64 is enough. And how we did that was we did sprintf, right? Sprintf, which allows us to format into a string buffer. And then we can use that string when we're calling other things. For example, like when we're calling draw string. So our destination is the buffer. Format string is, let me think here. We'll do %d sprites drawn in %f milliseconds. And we'll do n dudes. And here we'll do timer dot get time milli. And once we have our formatted string, we just do graphics dot draw string buffer. X and Y will just be 0. Font will be fixed cis, and the color will be red. D3D color underscore XRGB 25500. Red shows up nice both on black and white, so it's a nice choice in this situation. What's your problem? Not enough parentheses. Greedy fucker. And here we go, 60 sprites drawn in either 2 or 3 milliseconds is what it's saying here. Fair enough. And if we increase the number of sprites, we should see a corresponding increase in the time taken to draw them. Where is it? Game.h, I guess. So let's try 300 dudes. And here we have 15 milliseconds to draw 300 guys. Which is about right? Because I just increased the number of guys we're drawing by a factor of 5. So the time to draw them should also increase by a factor of about 5. And it has. Oh, it's actually gotten slower as we've been running the program. Strange. Runs a lot faster if I'm not doing my recording software. I can get about 700 guys on the screen without any slowdown. So you can tell when you're going to slow down if you think about it. If you do the math here. Let's do the math. Get out my trusty calculator. We're rendering 60 frames a second, right? So 1 second divided by 60 frames per second equals, so we have 1.66 or 1.67 milliseconds, no, 16.7 milliseconds per frame. That's how much time we have to render a single frame, 16.7 milliseconds, give or take. So if you're taking more than 16.7, then that means that you're missing frames. And that's not good. It's not smooth, right? So that's your goal. You want about maybe 15 milliseconds because you need a little time for your other calculations too. So you wanna give yourself a little leeway. Maybe 15 milliseconds taken for drawing your dudes, and the rest of the time just for, all the other stuff that you do in your game. Most of the time taken is in drawing, in most games and stuff like that. Alright, so that was our simple benchmark. I'm going to make it a little bit more complicated here, because if you look at it, it's going crazy here. We can't really see what time we have. It's going nuts. So what we're going to do is we're going to average our time over 60 frames. So we're going to take the average over 60 frames. So we need a float time sum. That's the sum of all the times over the current 60 frame period. And we also want to calculate in any 60 frame period, we want to know the minimum, the fastest frame drawn, and the slowest frame, because that's also important. So we want float we'll call this sometime, yeah. Min time, float max time. What else? And int frame count. I think that's all we need. Sometime, min time, max time. These are for the calculation. Now, we also want to display the results of the previous benchmarking period. So we'll need another set of variables down here. Float last min, float last max, float last average, because we're going to calculate the average from our sum. And that's it. That's all we need now. Alright, so let's use these. first we gotta initialize them. So here we go. Min time. We're gonna need some more variables here. # include what? What do I want to include? Float. .h. Float, I said. Yeah. Okay, so min time. We want to set it off to be float max, the maximum floating point number initially, and then once we start recording numbers it'll get lower, obviously. Max time, we'll start that off as 0. Average time is 0.0. And we want last min. We'll just start these off as 0. Fucker! Can never hit that 0 key. Last max 0.0. Last average 0. Fucker! Fuck you! There. And what was it? Frame count is equal to 0. Now I can't remember what it was called. Frame count, okay. Yay for memory. Okay, so that's all of our benchmarking variables initialized. Now, here we have start watch, stopwatch. That's fine. Buffer, we'll need that somewhere else. So the first thing we do is we go time sum plus and equals timer dot get time milli. Then we go frame count plus plus. Then we go if frame count is greater than or equal to 60. What we're going to do then is, what are we going to do? Then we're going to update our display variables, right? So last average is equal to time sum divided by 60, right? Last, oh shit, I gotta update min and max. I'll do that later. Last min is equal to time min. Last max is equal to time max. And then we gotta reset all of our calculation variables. So time sum is equal to 0.0 f. Last min, fuck you, min is equal to 0.0 f. Last max is equal to 0.0 f. And frame count is equal to 0. There we go. Now up here, we want time min is equal to, shit. We're going to do constant float time is equal to this. We'll call it frame time. The time taken in the current frame. Copy that into here. Frame time, we'll add that to time sum. Then we're gonna do last min is equal to the minimum of the current value of last min and the frame time. So if the frame time of the current frame is less than, fuck that, that's not last min, that's min time. Time min. Almost gave myself a nice bug there. Time min, right. So whichever one is smaller, the minimum up until now, or the current time. If the current time is smaller than the minimum up until now, then the minimum up until now becomes the current time. Time max is equal to max time max and frame time. There. So we update our minimum and maximum if they've changed, and then we increment the frame. And here, if we are at our 60 frame point, we update our display variables, and then we reset our calculation variables. And down here, we do the actual displaying. So, we make our buffer. We're going to do this over 2 lines. We'll say number of sprites $D and average render time %F. Actually, we're going to make it just 2 decimal points of accuracy, because after that it's all noise anyways, right? And we don't want timer that we want last average here. There we go. And copy that, paste it. Next one, we want average render time, minimum render time, max render time. There. And we'll just do last min. Last max. And here we want to change the line that we're rendering on, right? Because we don't want to render them both at the same position. So here we'll go, let's see, our font is 28 characters tall. So we'll go 28. And this should give us, that's weird. That's ugly, bro. You go over here now. I lost it. Whatever. Oh wait, I didn't lose it. I just made it super huge. Screw that. So I built it and it's failed. Time sum undefined. Alright. Okay, where's my game.h? Here it is. Sum time, min time, max time. Here I have time min, time max. Fair enough. Time sum. Time, fuck you. Time min. Time max. There. Are you happy now? Of course not. Warning, error, illegal member initialization. Average time, max time, min time. Alright. Why can't I make them all the same? Time min. Time max. Time average. What now? Game initial. Time average is not a... Isn't it though? Not a base or member. Ah, it is not. Touché, C++ compiler, touché. Fuck you. Brr. Damn it. I'm losing my perspicacity. That's not even relevant. Okay. So here we go. Number of sprites 200. Average render time 10.21, 23, 40, 48, 63, 35, 54, 11. Holy shit. Yeah, it's about that. You can see it it varies, but it's between 10 and 11 really. Actually, it's just gotten slower for some reason. I wonder if there's an actual reason why. Because it was running faster before, like demonstratively faster. Our min render time and our max render time are not changing. That is a problem. So let's fix that right now. Min render time, last min. Max render time, last max. Yeah, that would be a fucking problem, bro. Fuck. Time min. Time max. There. Build. There we go. So the minimum 0. What the fuck, bro? Max render time is working fine. So our worst frame is at about 13, 16, 15. Damn. Runs a lot better without Camtasia running, but what are you gonna do? Alright, why is time... Time min... Right, because we don't want... right. If we set time min equal to 0, we'll never get a time that's lower than 0, right? We have to set this one to float max, which is what we set it to up here. I could set it to some arbitrarily high number, like 10,000 or something, because we'll never get a frame that's longer than 10,000. But I set it to float max just because it's the biggest you can possibly get. If you're going to be arbitrary, you might as well be arbitrary in a non-arbitrary way. Yeah. Alright, so min render time. Yeah, it definitely shows that when we start the program off, it runs faster, and as we run, it gets slower. It doesn't really do this when I'm not running Camtasia, though. So here we're running. Now here's what I wanted to show you guys. Look at our average render time. We're at about 12.40, or let me just stop and run again. 11.5, 12. Minimum time is about 10.5. Worst time is 14 point some. Alright. Now, watch when I change it to release mode. Look at our speed now. It's rendering way faster. It's taking way less time to render. That's the difference between release and debug. So we use debug mode because it makes it easier for us to debug our program, right? But when you are actually distributing, you got to make sure you distribute in release mode, because release is way faster. Debug adds a whole bunch of nasty junk to your program to make it easier to diagnose problems. But it also slows down your program a lot, and it makes it a lot bigger. So in release mode, we're at about 5 milliseconds per frame. In debug mode, 12. 13 even. So that's what I wanted to show you. That's the difference between release and debug. And if I had my Camtasia not running, I could run it even faster yet, but yeah, so there's a little application of our text drawing abilities now. A nice little benchmark. Normally I wouldn't want to put so much code inside of my compose frame, but this is a benchmark, so we can't help it. We have to put it in here. We can't put our logic code. Where is it? In our Go. Where's Go? Here it is. In our Go function, like we would normally want to. It has to be where we're drawing, because that's what we're benchmarking. We're benchmarking our drawing code. Okay, so yeah, that's it. That's text rendering, font loading, and as a bonus, a little benchmarking. Also, that's how you use the timer object that I included. I always meant to use that object for benchmarking, by the way. So, the difference between timer and time, this time here, is timer is way more accurate. It uses, let me see if I can show you, timer.h. No, I can't show you, can I? Where did my fucking thing go? Wait a second. There we go. Got my Solution Explorer back. Here's timer, and it uses the performance counter, query performance counter and stuff like that. So the performance counter lets us have a incredibly accurate timer. It's like accurate to a few microseconds, maybe 10 or 100 microseconds. So we get microsecond accuracy here, and that's way more accuracy than you need to time game frames and stuff like that. But it's nice for benchmarking and stuff like that. All right, so have fun with text rendering and stuff like that. And when we come back, now I'm really going to show you guys dynamic memory allocation, because it's important and you should know it. So until then, don't do anything the chili wouldn't do.